concepts. What is mathematical induction? It's a specific method of proving propositions on expressions. So that would be such as 8 divides 8n. That's a very obvious, you don't actually have to use mathematical induction to prove that, but that is a proposition that you could use mathematical induction to prove, that 8 divides 8n, where n is an integer. Another one is that, a certain sum can be modeled by a general equation. And we're going to look at examples of those two, of sums and divisibility. So we often use mathematical induction to prove that a sum can be modeled by a simpler equation or a general equation. Instead of having to add up everything in the sum, you can have like a more basic formula that gets you to the end solution very quickly. Or we prove the divisibility of an expression. Now, the best way to learn mathematical induction is really just doing it. It's not... Once you get the hang of it, and I've done it for a long time, because a lot of you might also do it in university, in discrete mathematics, and maybe some other mathematics courses. So it is sort of a long-term skill for a lot of students that are doing specialist maths now, and you will just get better at it as you do it. You'll get more and more comfortable with it as you go. It's definitely a skill-based, practice-based type of question. So what do you actually do in mathematical induction? First, you do usually a basis step. So what you're doing in the basis step is that you prove true for whatever statement you're trying to prove true for the minimum value. So mathematical induction is done on a type of set that we call a well-ordered set. So a set is just a group of expressions numbers of anything, a group of anything, where each thing is a unique value. So in a set, you can't have two twos. A set of anything, a group of anything. Now, a well-ordered set is a set where there is a true minimum value. So if I said for all integers above 1, then there is a true minimum value because 2 is the smallest possible value. On the other hand, if I said for all real numbers above 0, there's no true minimum value because if I go like 0.0001, I can still go smaller. You can infinitely go smaller and smaller, so that is not a well-ordered set. So mathematical induction, we look at well-ordered sets, where we can get a true minimum value. So we want to prove true for the statement for the minimum value in the basis step. Then we do the inductive hypothesis. Now what we do in here is we assume true for k. So k doesn't really mean anything real. We're just making a statement basically that says this is true for k. And that will start to make sense in the next step, which is the inductive step. So in the inductive step, we basically say, okay, if it is true for k, then we can prove true. Oh, my mistake. Then we can prove true for k plus 1. Now what this means is we've proven for the minimum value. Then we can say that if it is true for k, k plus 1 is true. So that means we have the minimum value. Let's say it's 0. That means if k, 0, then it's true for k plus 1. So then it's true for 1. Now if it's true for 1, we then know if true for k, it's true for k plus 1. So now it's true for 2. And it sort of recursively proves itself as we move up. And that's what mathematical induction is. So we're going to actually, get an understanding of what all that means by actually, doing mathematical induction. Okay, so let's look at this real example of mathematical induction. We are proving that a sum can be modeled by a general formula. So this says 1 squared plus 2 squared plus 3 squared all the way up into n squared. and n can be any positive integer, it says, is equal to this general formula here. So that's 1 over 6 times n times brackets that say n plus 1, and then times brackets that say 2n plus 1. Now, this is very useful in mathematics because, okay, let's say we wanted to find the sum of 1 squared plus 2 squared plus 3 squared all the way to 10 million squared, as an example. Instead of manually having to actually like figure out each one of these and add them up using a calculator, of course you could use a computer to do it, but it's much more cheap in terms of time, even for a computer, to just use this general formula instead of doing 1 million operations, 10 million operations in this example of squaring and then adding all of those operations. Instead, we just do one single expression that explains basically all of those 10 million different terms. So that's sort of the use of mathematical induction with sums. Now let's do mathematical induction. So first what we're going to do is we're going to basically rewrite the statement, and you'll get very bored of rewriting the statement because you're going to be rewriting the statement at least slightly different each time, a lot during mathematical induction, but it's an important part of the process. So when you write a mathematical induction, it's sort of like, think of it like you're writing a single article, a single item. It's supposed to stand on its own two legs. You're not really writing it as though the marker knows what the question is, even though they do know what the question is. You're writing it more like an academic who is trying to write something that any mathematician could read without actually knowing the question and just understand what it's proving. And that's generally what we do for proofs. So that's why you rewrite this formula here, and this time you write it, or this set of expressions here, and this time you write it as let Pn be the statement 1 squared plus 2 squared plus 3 squared or plus plus n squared is equal to, then we have this general formula right here. So we rewrite basically what we're trying to prove. So now we're going to do the basis step. Now you don't really have to write basis step and induction hypothesis and such. It might be good to, it's your choice, it might help the marker a bit, but this is what I'll do to sort of give you an understanding of the process that we're going through here. So the basis step. Since we're in a well-ordered set, we can have a basis step where we use the minimum possible value. So in all the positive integers, the smallest value is 1. It's the smallest positive integer. So we should probably actually write something like consider P1. There you go. Consider P1. What does this culminate in? This culminates in 1 squared plus 2. 1 squared, sorry. Then we don't go any further because n is 1 here. Equals 1 over 6 times 1 plus 1, 2 times 1 plus 1. So that equals 1 equals 1 over 6 times 2, 3 equals 6 over 6. So left-hand side equals right-hand side. Therefore, we have our proof just of P1. Now we have to prove that it is true for Pk plus 1, where k is anything that we've already proven, basically. So that means if it's true for 1, which we've already proven, we can know that it's true for 1 plus 1. Now that means we know that it's true for 2, which means we know that it's true for 2 plus 1, and we have this recursive proof that we're building. So let's do the inductive hypothesis. So this is basically an assumption that we make that it is true for Pk. The reason we assume that is because then we can next say, if it is true for Pk, whatever integer k is, whatever positive integer k is, if it is true for Pk, then it is true for Pk plus 1. That means we have our recursive proof. So let's do it. Let's say assume true for Pk. I.e., so that is that 1 squared plus 2 squared plus 3 squared, all the way up into, this time, k squared, is equal to 1 over 6 k, k plus 1, 2k plus 1. Okay. So it's basically the same. We rewrite this once again. This time we use k because we want to separate it from n. We don't really want to assume that it's true for n, because if we did that, we're assuming that it's a little bit dirty looking, I guess, because we're assuming that the statement is true to prove that it's true, which is a bit absurd. So we just give it sort of a level of separation by putting k in there instead. And that's the induction hypothesis. Now we're going to do the inductive step. So we're going to consider pk plus 1. So we're going to consider pk plus 1, and we're going to use our assumption of pk to prove pk plus 1. Now we're going to do that on the next slide. It's probably going to be doing a little bit of going back and forth, unfortunately. Let's consider pk plus 1. So that is, we have 1 squared plus 2 squared plus 3 squared plus ... all the way into k squared plus k plus 1 squared. Technically, you wouldn't have to write this down, but it's good to write that down because it sort of keeps a connection with our assumption that we made for pk. And you wouldn't have to write it down because if we go all the way to k plus 1, then we can assume that k squared could be in the ... if we didn't write it down. So then we're going to say that equals to 1 over 6 k plus 1, because we're going to basically just put k plus 1 everywhere where there was a k. K plus 1 plus 1. 2k plus 1 plus 1. So now what we want to do is we want to figure out a way basically to get some components of this whole equation here. Oops. And if we can equate those components, if we can get some of those components and we can equate some of those components to something in here, we might be able to create a proof. And as you do induction, you'll sort of get a hang of this process. Somewhat, you're going to have to learn to actually build an intuition for this, to be honest. That's why this is, like, I think more than any type of question you're going to do, this is a very practice-oriented type of question to learn. But our example still stands. So now what I'm going to do is I'm going to concentrate on the right-hand side. Since I want it to sort of look, I want to basically get some component of this over here in here. I'm going to try to keep some things. So I see there's k plus 1 here and there's k plus 1 here. So I'm going to try to keep that. I'm going to try to build this whole right-hand side as a component of this right-hand side here, and we'll see where that actually gets me soon. So this is k plus 1, k plus 1 plus, we'll just change it to 2, and then 2k plus 3, all over 6. So now I want to keep the k plus 1, but I want to expand these brackets on the right here. Say 2k squared, so that's k times 2k, plus 3k, plus 2 times 2k, so that's 4k, plus 2 times 3, which is 6, all over 6. And I want to simplify it a little bit. K plus 1, 2k squared, plus 7k plus 6, all over 6. Okay. So I'm already starting to see some patterns that remind me of this situation over here. So we have the 2k plus something. This time we have 2k squared. So if we were able to take the k out of this over here, we would be benefited because we'd be able to put the k at the front. And basically, we're looking for patterns that we can try to replicate through troubling, challenging algebra. So I'm going to, a lot of the time when you're actually doing this on an exam, you will be writing lines and lines, and then you'll realize that they got you nowhere and you're going to cross them out. This is a pretty simple induction. I've seen it before, so I'm a little bit advantaged by partly remembering the process, but don't be discouraged if you try to move things around and it doesn't immediately get your result. That is what you should expect. You're going to have to try to move things around a lot in specific ways until you find something convenient. If you're really stuck, maybe consider that you've made a mistake earlier, so it's completely impeding you from moving forward. And that is something that's really punishing about induction questions. It's really hard to get those carry-through marks because you can't finish at a proof if you've altered the statement so it isn't even actually true. So there's challenges there, but here I'm going to try to, so I want to get a K. I want to take the K out over here. I'm not going to be able to take the K out of this set of brackets because there's a 1 there. I'm not going to be able to take it out of this set of brackets yet, but maybe I could remove, and I want to keep that 1 there to be clear, but I don't necessarily want to keep this 6, and I don't want to keep this 7K because they don't look anything like anything that I have in this equation over here. So I'm going to play around with things a little bit. I'm going to say plus K because over here we do have that plus 1, and remember I want to take this K out of this set of brackets, so everything's going to be divided by K. And then we have plus 6K plus 6 all over 6. Now I can remove these from the brackets. If I go K plus 1, 2K squared plus K all over 6, and then I can remove these. Let's put them in their own brackets for a moment just to make the working easier. I can remove these to their own set by multiplying them with everything in the other sets of brackets. So that becomes 6K plus 6 and then multiplied by K plus 1. So maybe just look at it for a moment if you're a bit stuck with that, but these are actually equal. I can basically take this out if I multiply it by everything it needs to be multiplied by. So now we have these two sets. Now, if we go up here and work it out a little bit more, we can take the K out of this set of brackets now, which is what I was trying to sort of move towards. So then we end up looking like this, over 6. And then we have a plus, and then we can take 6 outside of these brackets, so it's a 6K plus 1, K plus 1, all over 6. So then this equals to K plus 1, 2K plus 1, all on 6, plus K plus 1 squared. So this is where we want to be. We basically have this left side over here, this right side, sorry, we've created that. That's the same as this. And then all we have is an extra K plus 1. So then I can say equals, since we have this right side here, remember this right side is equal to that. So then I can say equals 1 squared plus 2 squared plus 3 squared plus dot 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 plus K squared, because this side is equal to that side, and then we have this extra plus K plus 1 squared. And now our equation actually looks exactly like this over here. So our proof is done. We have left-hand side equals right-hand side. So it can get pretty hard in the middle, but I think it is a situation of if you practice these a fair amount, you will start to get a sort of intuition, a sort of sixth sense as to how we can actually move towards a solution here. Basically, and we'll see this when we do the mathematical induction for division, we use this assumption of PK to prove PK plus 1. So now that we've proven left-hand side equals right-hand side, we will write something of this form. Some teachers teach you a really specific way to write it that you can just memorize, so it's easy. I'm going to write it like this. We have proven Pn is true for P1, and if true for our assumption, which is pk, then true for pk plus 1. Therefore, we have proven by mathematical induction. Okay, I'll do it like that. So basically, this just is a little thing that you should always put at the end of mathematical induction to explain what the process is. You said, okay, we have proven that it is true for 1, and we have proven that if it is true for any value of k, if it is true for that value of k, such as 1, then it is true for k plus 1. So we have proven for 1, therefore true for k plus 1, which is 2, because 1 plus 1. Then if it is true for 2, then we've proven for k plus 1, so it is 2 plus 1, so it's 3. So we've made a proof that, recursively proves itself for infinity, which is a very beautiful thing.